we're going to be taking a look at quadratic functions and equations, but we're going to specifically try to write them. So given certain values, given certain coordinates, given certain characteristics about the graph, we're going to come up with the functions. Now, what we've used so far are just 2 of the 3 different forms. Okay, so if you recall, remember there were 2 forms. We've done vertex and standard. The third form from today I'm going to take a look at is going to be called what I like to call just like root form. Another way to think about it is also known as intercept form. Okay, intercept form. Why do you think this is called intercept form right here? Like, you know these 2 already, right? I hope we're all familiar with these at the top. Okay, that's standard form, and there's vertex form with the k value moved over instead of being over here. The k value is moved over. But why do you think this is called root or intercept form? Why do you think it's called root or intercept form? Max? It shows you the intercepts. Very good. So give me, for example, here, if I had the following. All right, so there's my function, right? If that were the case, what could you tell me right away about the x-intercepts? About the x-intercepts. Max, go ahead, follow. 4, -1. How does you know this? Well, to find the x-intercepts, you set y equal to 0, which gives you this. And then when you solved an equation like this, well, we've been doing this all year long. This is just a quadratic equation. The 2 has no effect. I get 0. I'm sorry, let me just do it with I'll go right into my table. I get here thinking x minus 4 equals 0 and x plus 1 equals 0, just like we've done all year long. So this gives me the x-intercepts when it's in factored form. So there's a tendency to call this intercept form or root form. You can even just call it when it's in factored form. It's not really like a third case because technically speaking, a lot of you will recognize that when it's in standard form, you can probably get it to be in this form if it's factorable, right? When in standard form, if it's factorable, you would probably write it like this actually. So I'm calling this intercept form, but this is not something new. This is something that you should know already from what we've done. Do I want to go into some crazy details about B and A? I guess I do. Okay. So one thing that I show what's called the sum and product of roots. So let me talk about this for a little while. So if I take a look at the following, if I look at this right here, and if I were to multiply it out, what would it become? Okay, multiplying this out. I'll leave the A out in front. What do I get on the inside if I were to multiply this out? As if they were numbers. As if they were numbers. Now they're R1 and R2, but imagine those are numbers there. What would I do if I followed it out? What would I get? Sorry.
So you have x squared.
Go ahead.
Plus 2xr, and then...
Close. They're different numbers. R1 and R2 are different.
Oh, then plus 2xr1, or is it x r2?
You're on the right track.
Around there, I'm thinking of...
Outer, right? Do outer next. Remember FOIL? You did first. Do outer.
Then you have x minus xr2, and then minus xr1.
From the middle gives us minus xr1. Keep going.
And then you have r1, r2.
Now, what's r1 times r2? We just leave it that way, and it's a positive because it's 2 negatives multiplied. So that's what you would turn out getting in this problem. If I were to FOIL that out, I'm just showing you this as a proof of something, and I'm going to explain in a little while. Remember we talked about, you guys did this in a homework recently, and you were all wondering, like, when would it be used? We talked about sum of roots and product of roots in that problem with C and A and B and A. We're going to show it here now. So if I look at a problem like this, I can now take a look at the middle terms, and I can recognize that both of the middle terms both have an x in them, right? So if I want to look at this, I could say, this is really the following, and it's hard to see this. R2 plus R1 times x. And see where this comes from right here. So look, see how there's, in this case, R2, and in this case, R1. If I take out a negative out of both of these, they both become positive, and that's this negative I took out here. And if I take if I take x out of both of these, which goes here, I'm left with R1 plus R2. If I were to distribute this x, this would go back to xr2, xr1, and the negative would make both of these negatives. So I'd get back to this right here. So all I'm doing is factoring out technically a negative x in both cases. Except I'm putting the x over here. Instead of putting the negative x out in front, I'm putting the negative here and the x here. Why do you think I might be doing that? Why do you think I might be doing that in this problem? What does this look like now? What might you call this? What's a word for something that goes in front there? Yeah, this is like your coefficient now. Okay, this is like your coefficient. So what you're going to recognize is that this, technically speaking, is the sum of both roots. And this is the product of both roots. So if you recall earlier, we talked about C over A and B over A and all this stuff. Well, if we look at this problem, we recognize here, well, if I distribute the A to everything, okay, if I take A and distribute it out, I get the following: ax squared minus, then this is going to be A times the sum of roots, and then at the end we're going to have an A times the product of roots. So all I'm doing now is taking this A value, distributing it out to all three terms in the quadratic. So if you look at this and we say to ourselves, well, this right here, that's really B. And this right here is really, thank you, ax squared plus bx plus c. Do we see that? This is really like a plus bx in the middle here, because this x really comes up. There's really a bx here. So this is really in standard form. It's in standard form because I see ax squared plus bx plus c. So this entire thing is plus b. This is what b is. So I could say to myself, well, inherently, b is equal to negative a times the sum of roots. That's what this is right here. And then from this statement, I could say, well, c is just a times the product of the roots. I promise we're going somewhere with this. Well, what does this enable me to do? I could solve for the phrase sum of roots. If I were to solve for this, how would I get rid of negative a that's in front of it? How do I get rid of negative a? It's in front of something. What operation? It's currently multiplying. Right? Negative a is multiplying by sum of roots. I want to get rid of negative a, so I divide. So I get negative b over a is equal to the sum of roots. Okay, or you can put b over negative a. It doesn't really matter, right, where I put the negative. And then if I want to get rid of a on the right-hand side over here, I also get rid of a by dividing. I'll get c over a is equal to the product of roots. Now, if you go back to that homework and you look back and see what you did with that, you verified this actually already. You showed it. This is just what's called the derivation, where it comes from, the root of this concept. So this idea comes from actually evaluating using intercept form, multiplying it out into standard form, multiplying the a out, and then coming up with the fact that, well, this is really just b. So set b equal to this thing. This is negative a times the sum of roots. This is a times the product of roots, and that's c. So set those things equal, and then solve for sum of roots, solve for product of roots. So if you have an answer, and you actually, whatever the equation is, right, you get, and you take the answer and you add the two answers together, whatever you get will be equal to negative b over a. If you were to multiply your two answers together, it will be equal to c over a, always. So for example, to show you what I'm talking about here, if you had something like the following, I'll make it very easy. What does that factor into? Come on.
X plus 3, x plus 1.
Thank you. So as a result, my roots are going to be negative 3 and negative 4. Those are my roots or x-intercepts, right? Well, go ahead. Multiply those two things. What's negative 3 times negative 4? 12, right? So the product, according to this, is equal to 12. Well, what's the product according to our rule? C over A, right? C is 12. What's A?
1.
12 over 1 is just 12. So we can check our answers with this method anytime we'd like to. We could also sum them together. Sum them together. What do you get when you add these two things together? So the sum is equal to negative 7. Well, according to what we saw earlier, we were told that the sum is negative b over a. Well, negative b is negative 7 over 1. So the sum is indeed negative 7. So if you memorize these rules, you could always check to see that your answer is correct. Or given those values, you could actually come up with a function. If you knew what the sum of the roots are, the product of the roots are, you could come up with your function a little bit easier.
So like the whole formula is just used to assist, like if you have it regular, like
If you already have the roots, maybe coming up with a function, or when you get the roots, checking if they're correct or not.
use the other thing to like find negative b over a and c.
Yep. So if I needed to, like, let's look at the first example to prove where we use it here. So if I wanted to find a quadratic with those roots, it's almost impossible to do it because they're imaginary. Right? If I gave you the roots, look what they are right there. Come up with a function that gives you those roots. Good luck doing it, right? You're going to have to do this. Technically speaking, this is what you'd have to do. Right? That's what it really is. That's what this is telling me. That's what the function is. If these are the roots, if the roots are 3 plus I over 2, then this is what the factor must be to give me that root. And this is what the factor must be to give me that root. That's really messy to multiply this out. I could do it, but it's just annoying to have to go through the process of foiling. So instead, all you got to do is sum and product of roots. So we start by finding the sum of roots. Let's add them together. When I do that, I notice, oh, look at that. Coincidentally, I already have a common denominator. That's very nice. So if I have a common denominator, I know that I just keep the denominator and add the numerators. 3 plus 3 gives me 6. What's I plus negative I? So the answer is just, so the sum of roots is just 3. Okay, let's hold off on that for a minute. Let's get to the product of roots now. If I were to multiply these two things now, denominator, what do I get? Good. Please don't just carry the 2. Actually multiply, very good. Multiplying the top, they are both complex conjugates of one another, right? So as a result here, I don't have to worry about really foiling too much. The outer and the inner, what happens to those terms? They cancel. The middle terms cancel. So this will become 9 plus 3i minus 3i. Those don't matter. And then minus I squared. What's I squared, though?
-1.
So this is 9 minus negative 1, which is really 10. That gives me 5 over 2. Now, here's all I know so far. And the question said, come up with something with integral coefficients. First of all, what the heck does integral mean? Integral, in this case, it means something different than calculus, by the way. But integral coefficients means the coefficient should be what? Integral sounds like what kind of word? Integer. It does also sound like integrated, yes. Integers. So we're looking for A, B, and C that are integers. Well, what was the rule? What did we say a minute ago? Product of roots was equal to what? What was our formula we wrote down a minute ago? The product of roots equals what? That was the sum of roots. Got that? Good. Okay, I'll write that first. What was the product of roots? What was the product of roots? C over A. So tell me, what do you think C is? Just look, literally look, equate. What does C, you think? And what do you think A is? 2. I'd agree with that. So let's make C 5 and let's make A 2. Well, if that's the case, if A is 2, go ahead and plug a 2 in up here. Right? Take a 2. Now that you made A 2, plug a 2 in there. And what do you get for B?
Or negative.
Negative 6. And this should equal f of x, not 0, because I said come up with a function, I think, right? Did I say function? Yeah. Oh no, quadratic equation. Never mind, we're good. I said equation. So take a look at this. It's not obvious right away because you're going to think B is 3 from looking here. Follow my cursor, please. You're going to think, oh, B must have been 3 because the 3 and the B is here. But in reality, remember that A is 2. We said that because of this. Look at this right here, and this is the part that you need to start with. You have the A value already because it's a 2. So if A is 2, in math, I would put a 2 right here. I would multiply by 2, which gives me 6 equals negative B. Again, the 2 here multiplies over to be 6 equals negative B. So B is just negative 6. George.
I know 10 over 4 is 5, but how do you know like it's not C equals 10 and A equals 5?
You could do that. And then your answer would look like this, George. Are those any different? What's the difference between the second one and the first one?
It's just multiplied by 2.
So in reality, if I were to find the roots, wouldn't those have the same roots, it turns out? So if I were to solve a problem like this, I could factor a 2 out of the second equation and then solve, and I would get the same answers. So the only difference is that these graphs, if you were to physically graph them, one would be taller, the other one would be shorter. It would be stretched vertically because of this doubling of everything. All the y values would all be doubled. So the graph, if I were to graph these two functions, well, these have imaginary roots, but hypothetically speaking, right? The first one would look like this, the second one would look like this. But what do you notice? That's ugly. But what do you notice about the roots or where it crosses the x-axis? They cross at the same location. So neither problem would be correct. Now, theoretically, if it says integral coefficients, either are correct. But you should have your answer in simplest form. Okay? And it said integral coefficients, so can I divide everything by 2 here?
No.
What's it going to do? It's going to cause this to become 2.5, which is not an integer. Okay? So I go with C over A to help me. Make this C, make this A. If I know A is now 2, I plug that 2 in and go ahead and get B. Can we do another one? Are we good so far? All right. The second one says, find the roots of this and check your answer. Find the roots and check your answer. What's the quickest way to find the roots of this? You could try and factor, yeah? That's one way. If it doesn't factor, what do you go to?
Put it into the root form.
Yeah, put it into...
Then
You could he said factor, so you could try and factor into your root form, but if that doesn't work... Complete the square? What else could you do? Quadratic formula. Either one, right? Completing the square or quadratic formula, they're both just as quick. I would use the quadratic here. It doesn't matter. So if you go to solve this, we're going to get negative b plus or minus the square root of b squared minus 4ac. That's going to be 41 all over 2a. Those are the answers you're going to get. I'm not going to go through the quadratic formula. You should know how to do this by now. It's not the time we're spending today on that. So those are the answers you're going to get. So read what it says. It says check your answer just by using the sum and product of roots theorem. Well, go ahead and sum these. Here's the sum of them, right? That's how I would sum them together. Plus or minus means I have 2 roots. So one has a plus and one has a minus. We have 2 different roots here. One plus and one minus. So when we add the numerators together, we're going to get negative 1 plus negative 1, which is negative 2. The denominator is still 4. What happens to root 41 and negative root 41? They cancel. So I get negative 2/4, which is really negative 1/2. Well, we were told that this was the sum, and if you recall, the sum is represented by negative b over a. Does it hold true? Look at the original function. Do negative b over a. What do you get when you do negative b over a? B is what? A is? So negative b over a is negative 1 over 2, right? And what did we get as an answer? Negative 1 over 2. So a way to check that your roots are correct is by summing them together. The 2 answers you get, sum them together, get an answer, and see if this answer is the same thing as negative b over a. And in this case it is. That would be negative 1 over 2, and that's what we got as our answer when this gets simplified into that. What do you think the product of roots is going to become? Come on, use the rule. What's the rule? Product of roots equals?
negative 5 over 2.
Very good. The product of roots is C over A. That's what we came up with earlier. C is negative 5, A is 2. So this better be negative 5 over 2. So if you were to multiply these two things now, do the exact same thing, but just put a multiplication sign now. Do I care about the inner and the outer terms again? What's going to happen? It's binomial conjugates here. The last one were complex conjugates. 4 times 4 is 16. The numerator is going to give me negative 1 times negative 1, which is positive 1, minus root 41 times root 41. What is that? Thank you, George. Don't actually multiply the numbers, right? Please recognize that like root 3 times root 3 is really root 9, which is just 3. Obviously, when you multiply a root by itself, it goes away. So we're going to end up with what looks like negative 40 over 16. Divide both of those by 8 to reduce. You'll get negative 5 over 2. Same thing that we said we should have gotten up here for the product of roots. So again, this is literally a means of coming up with a function like we did in example 1, or simply multiplying the roots and summing the roots to check that your answers are correct. So it's either coming up with a function or checking that your answers are correct. Either one for this. Questions? Okay, that's it for sum of roots and product of roots. We're going to move on in this section to something that's a little bit different. So that's all we're going to do. It's sum and product of roots. That's really all you need to be able to do. If you can do 1 and 2 of these, you should be fine, okay? So let's take a look at number 3. This is where it takes, remember I said it all comes together now? This is where it all comes together now. Find a function whose minimum value is negative 3 and whose graph has x-intercepts at 1 and 3. Now, if you don't know where to start, what do you think you might want to do to start? It makes it a little bit easier to visualize. Please draw this. X-intercepts of 1 and 3. Boom. There's 1. There's 3. 1, 2, 3, 4. Okay? Now, the minimum value of a graph. What is that? What does that mean, the minimum value? This is where vocabulary comes into play. Mr. Ryder.
The minimum value is like the vertex like at the bottom.
Very good. That's exactly right. And where do you know the vertex is? This way. Where is it always?
It's in the middle.
Good. It's always between the roots, right? So the vertex has to fall along this dashed line. What do we call this dashed line, everybody? The vertex has to be there. And since we know the min value is negative 3, boom, there's the coordinate right there. If you're given the minimum value, that means you're given the y-coordinate of the vertex. Remember that. That was last class. Minimum or maximum value is the y-coordinate of the vertex. So I know already that that coordinate is negative 3. Now, because I know that this coordinate is 3, 0, and this coordinate is 1, 0, what must the x value be for the vertex, obviously? It must be 2. 2 is equidistant from 1 and 3. What's another word for equidistant? It's the midpoint. 2 is the midpoint of 1 and 3. Everybody sees that, right? We all understand that mathematically? How do you get 2 to be the midpoint? How did you actually figure that out? Did you just look? What could you do when you want to find a midpoint? What's the word for that? In general math? What's the word? How do you find the midpoint of 2 points? Come on, add them up and by. So what are you finding? The average. Jot that down. The average of the roots, or the midpoint between the roots, is the axis of symmetry. X equals 2 is the axis of symmetry in this problem because of the fact that we know 2 is the average of 1 and 3. So that's my sketch already. So if I were to actually draw this graph, here's what it would look like. There's the graph. I already have it drawn. But it doesn't say to draw it. What does it say to do? What are we trying to do? Find the function. Yeah. Equation, the function in this case. So we have f of x instead of 0 equals. So we know it's going to be f of x equals. Well, I could do this 3 different ways and come up with the same answer. I could start with vertex form because I got a vertex. Right? Look, there's the vertex, right? So I can start with vertex form and plug in one of the points to get A. I could actually, if I wanted to, use standard form. Standard form, I've got 3 coordinates, so I could find A, B, and C. 3 coordinates, 3 unknowns. Or I could use intercept form because I've got both intercepts. I'm going to do it all 3 ways. You got to follow along. If you want to just watch for a little while, because I'm going to go a little bit quick through this, you can watch and then maybe write a little more down later. But I'm going to go through all 3 methods. So here's intercept form. I know the intercepts are 1 and 3, so those already go in here and here. So So I already got that much. Now, the third coordinate was given as, here's what I'm visualizing. Please visualize this. Cover these up. These have already been used. They're done. What's the last coordinate? 2, -3. So plug 2 in for x and -3 in for y and get A. Again, the only missing variable, remember, how many unknowns do you have here? 1, 2, 3 unknowns. 1, 2, 3 unknowns. How many coordinates did I give you? 1, 2, 3 coordinates. 3 unknowns, 3 coordinates. You're going to notice, pick up on that pattern, except for the vertex case. It's the only exception. So if we want to get A by itself, A is just going to be 3. So one way to write this function is as follows. There's one correct answer for this problem in intercept form. I don't specify what kind of form I want this function in. So you can leave it like that in intercept form. I'm more than happy with that. You can multiply it out and put it in standard form. Multiply x minus 1, x minus 3 out, put it in standard form. That's one way of doing it also. You could also find standard form by using your general standard form function. And we did this last class. I'm not going to go through the process of all of it, but plug in all 3 points. If I plug in the intercepts, I'm going to have 0 equals a times 1 squared plus b times 1 plus c. 0 equals a times 3 squared plus b times 3 plus c. And then if I plug in the last coordinate, I have -3 equals a times, and what was the last coordinate? 2 comma -3? 2 squared plus b times 2 plus c. How many equations do you guys all see here? How many? How many variables? So what is it, A? Matrix. 1, 1, 1, 9, 3, 1, 4, 2, 1, and then take these 3, 0, 0, -3. Okay, I can solve this by matrix method. I will get an answer that says the following. If I solve it by matrix method, I'll get the following. F of x equals 3x squared minus 12x plus 9. A will be 3, B will be -12, C will be 9. Now, how do I know that this is right? I could actually even multiply this out and check, or I could use my rule, sum and product of roots. The sum of the roots, go back up, add them together. What's 3 plus 1? 4. The sum of the roots is 4, the product is just 3. Well, the product told us to take C over A. 9 over 3, well, that's just 3, and the product was 3. The sum, we're told, though, in this case is 4. Well, that's -B over A. What's -12 over 3? -12 is 12 over 3 is 4. And that's the sum of roots. So you could check with the sum and product of roots that these are correct also in this method here. Am I about to run out of time? Okay, please just wait till the bell rings, guys. You don't have to rush. I know you might have lunch, but give me a second. The third way to do this is with vertex form. Now, if I know the vertex is 2 comma -3, I could plug that in for h and k. That's the vertex form. And then if I want to get A, I could use either of my coordinates. Remember, I had these coordinates for the x-intercepts. Those are my x-intercept coordinates. I could plug either one of these in and get the A value. Now, listen carefully because I know you need to go, but tonight,